All right, guys, so for today, we're just going to probably polish off everything to do with graphing today and its applications, right? And the derivatives applications in graphing. And then tomorrow we'll look at, we'll revisit some stuff with actual word problems and applying derivatives to word problems, okay? But first things first, like this is kind of a warm-up question. We've been nice here. And we've given you the derivative and the second derivative. What we want to do is just determine the intervals of the function, increasing, decreasing, and then for part 2 is concave up or concave down. Okay, so it's just almost like a recap of yesterday and how you guys should be setting this sort of thing up for looking at the graphs of these polynomial functions, if you will. Okay, so we know right off the bat, just to reiterate, for a max or min, you know, we're going to set the derivative equal to 0. Oops. The derivative function itself is equal to 0. Okay. And so we're going to see the derivative function, if we set that all equal to 0, well, the 0 would consume the denominator. So the only thing we're worried about is the fact that we have negative 4x is equal to 0. And so x is going to equal 0. Okay. So this is our like turning point, if you will, or like our turning point, I shouldn't use that word, maximum or minimum, right? And so we want to look at the intervals for x less than 0, and we want to find, and we want to look at the interval of x is greater than 0. Okay? If we were to plug in a value less than 0, so a negative number, we would see that the function, or the derivative, the slope of the tangent, sorry, the slope on the function would come out to be positive, which would indicate that the function is increasing. If I were to plug in a negative value into this function, right? Or sorry, specifically the slope. Okay, if I plug in a negative value here, I'm going to see that it's going to come up to be positive, right? And the opposite would be true if I plugged in a positive number, right? If I plug in a positive number into the slope equation, right, the first derivative, I'm going to see that I get a negative, and so it's decreasing on this interval. And so we could conclude okay, this is just kind of a warm-up question for you guys. Increasing for x is less than 0, or this could be new for you, right? X is a part of the real numbers as long as it's between negative infinity and 0. Okay, and then we could also say decreasing and decreasing for x is greater than 0. Okay, or we could say x is a part of the real number such that 0 and positive infinity. Okay, so that's us dealing with the slope and finding where the graph would be increasing or decreasing, the slope, right? Or it's, if you wanted to relate that as a function of like position and velocity and acceleration, you would see that the velocity would be increasing in the negative x values and then decreasing for the positive x values. Okay, so then yesterday we looked at something else. This is again just kind of a recap. So for points of inflection, right? Remember, points of inflection, you know, they're the transition points between like a positive or a concave up and concave down, right? So we're just going to try and find if there is one that exists, right? So to do that, we know we have to set the second derivative equal to 0, right? When we do that, same idea, the denominator is going to get consumed by the 0, and so we're going to get 0 equals 4 times 6x squared minus 1, okay? And then we can see, okay, well, 0 is going to consume the 4. That doesn't matter. Then if I were to say, okay, well, I'm going to bring the 1 over, I'm going to get 1 equals 6x squared. So 1 over 6 is equal to x squared. So x will equal plus minus root 1 over 6. Okay, so we have 2 inflection points here, right? So on the interval, right, you got to picture what's going on here. We want all the values that are to the left of, let's say, the x will equal positive 1 over 6. Okay, so there are 2 inflection points. So we want to look at all the values to the left of the negative inflection point. So we can say, okay, well, x is less than negative 1 over 6, the root of 1 over 6. And then we can look at, okay, well, what about, what's the graph doing, concave up or concave down between the 2 inflection points, right? So we could say, okay, well, between okay. And then we could say, okay, well, what about to the right as well, okay? Okay, and you guys, sorry, I should have probably just written it like this. Save yourself some headache. You can square root 1, so you could just write 1 over root 6. Okay, there you go. Okay, and so if we were to check what's going on here, right? So if I were to plug in a value to the left of 1 over, or to the left of negative 1 over root 6 into the second derivative function, right? Then we would see that our second derivative would come out to be positive, which would indicate that the original function would have been concave up. And then for a value in between the 2 inflection points, I would see a negative, right? For instance, you could plug in 0, right? I would see, if I plugged in 0 into the second derivative, I'd get negative 1 over 1. And so it comes out to be negative, right? And so I get concave down. Okay. And then if I were to plug in, I guess, any positive value, right? Greater than 1 over root 6, I'm going to see that it comes out to be positive again. And so we're going to see concave up. Okay. And so you can draw all those same conclusions from above about the original function, right? You could say f of x is concave up on this interval, concave down on the middle interval, and then concave up again on the last interval. Okay, so I'm going to let you guys have a look at this. Okay, this is in your note as well. I'm not going to go too much into that. I'll stop the video here, and then we'll go down, and we'll basically do the same thing this time with a more, well, not even a more complicated example. We're going to find a derivative of this, the first derivative, second derivative, and we'll produce what the picture or the graph is supposed to actually look like, okay? And that'll be the second part of this morning's lesson, okay? Just how to actually, finish off these kind of questions, okay? So I'll stop the video here, and I'll see you in part 2.